thank you everyone for coming today. It's kind of a weird time with that virus going on, but so thank you again for taking the time. So we are happy to see that many of you have chosen to register for this first webinar. We're about 30 people, so that's great. I'm Nicolas, Technical Manager and Business Executive, the Business Development Executive. And with me today is Sergio Rodriguez. He will be leading the presentation. So I'm just making a short introduction and then hand it to Sergio. So the topic for today is induction heating. We have also received new ideas from some of you, and thank you very much for that. We will do our best to address these topics in the coming webinars. So stay tuned. We will update with the information for the next webinar. So last point before we start, mentioned in our email, we want this webinar to be interactive. So please do not hesitate to use the chat feature to ask your questions. We have muted everybody on entry so that we have a clear webinar. So I will monitor the questions and we will answer on the go as much as possible. Okay. So now I'll let Sergio, our technical support engineer, lead this webinar. So Sergio, please go ahead.
Okay. Hello, everybody. As Nicolas said, we're going to introduce induction simulations. We are using this topic because in most trainings I've been doing, I see people don't really know we can simulate this type of process. We are trying to give more awareness to all the modules we have in Forge. As you know, you don't have to pay any additional money for this. It's all included in the package. And it's a good way to test virtually if this could be a good solution for your company. Okay, so I'm going to start with a quick introduction. For those of you that don't know what induction simulations are, we're going to basically have a inductor. We're going to apply some alternating current to it. And this is going to create a magnetic field. It's represented here in red. And if we have a conductive material inside the inductor, it's going to create an induced current on it. And it's going to generate heat by Joule effect mainly. Okay. This is going to increase the temperature in the billet really quick. I'm just going to give a quick introduction, by the way, because induction is quite complex multi-physics process, so it has a lot of background to understand what is happening exactly. The main advantages for this, the main reasons for your company to maybe be interested in this process is it allows us to heat really precise areas. It allows us to be really accurate in the areas we heat, and it let us reach high temperatures in a really, really short time. It also allows us to repeat the same process accurately and increase productivity in most cases. It's really quick to start up and switch off. The energy, it has a really high efficiency. The main problem or the main disadvantage of this is that it's a really complex process, multi-physics, and it requires some coupling to do in the solvers. I'm going to give an idea of how we do it in Forge. It has a lot of applications. I don't have time to get into this in detail, but the main applications are preheating before the manufacturing process. Also, you can heat during the manufacturing process, for example, between stages. You can reheat the billet to make sure you are above a temperature. And also there are a lot of applications for localized heat treatment after the process is done. Going back to the solver in Forge, we're going to be using two solvers and we're going to couple them. So we will start with the we'll have the thermomechanical solver, the one you are familiar with, the one you use for most of your Forge simulations. And we have added this Forge induction electromagnetic solver. So how the induction simulation works, we'll start with solving the Maxwell equations to get the electromagnetic parameters. Once we have obtained those, we will import these parameters in our traditional thermomechanical solver. With this, it will allow, we can run a heating simulation in the standard way that we are used to. We will get the heat source from the electromagnetic parameters. And with this, we will be able to solve the thermomechanical equations. The thing is, we need to couple these two solvers because it's not enough to get the first parameters in the electromagnetic, in the Maxwell equations, because these are normally dependent on temperature. As we're going to be increasing the temperature really high in the thermomechanical solver, we will have to go back to the electromagnetic solver and update these parameters for the new temperatures. In case we have a material with electromagnetic parameters that are not changing with temperature that much, we don't need to go back to update these parameters. But the standard workflow is going to be get the initial parameters, calculate the heating simulation, and update the electromagnetic parameters with the new temperatures we will obtain. So the fact that we have two solvers will lead us to have two different simulations in the preprocessor. We will have the standard simulation with the workpiece. It's really similar to a standard heating simulation. I will show a practical case now to show the difference. And then we'll have to add a new simulation that requires to introduce a new concept. It's what we call the global mesh. To calculate all the electromagnetic parameters, we will need to mesh the air between the inductor and the build, because there is where we will be creating the magnetic field. It's where most of the phenomena happen. So we will have to mesh the air and then create a new global mesh that is basically a combination of all the meshes you are seeing here. I'll show it in a real case now. A question that I get a lot when I introduce induction is which parameters would I need to start simulating this? And the answer is you don't need a lot, but some of them might be a little harder to get. We basically need the electric resistivity and magnetic permeability, dependent on temperature again, for the material. I'll show some details about the materials in Forge and the possibilities we have. And also for the inductor, we will need the frequency and the current on. There are some alternatives to this that I will introduce later too. For the thermal simulation, we need just the standard thermal parameters. I'm going to assume everybody is familiar with this. For the materials, getting into detail now, these are the traditional materials we'll have in the first version of the induction simulations. Basically, for the thermal simulation, you will use the standard Forge materials you've been using so far. And then for the electromagnetic simulations, we have special templates for them. We have several in our database. We have expanded this a lot. So if you want to tackle the simulation and you don't find the material files you need, please contact us. We will help you and assist you. But yeah, other than the templates we have, now in the new version, we have added this new feature. We have partnered with JMAT Pro, not only for the standard materials, also for the electromagnetic parameters now, we can export directly in GEMA Pro the magnetic permeability and electricity resistivity as a function of temperature. So if you happen to have GEMA Pro, it will be really easy to start doing your induction simulations because you already have all the material information you need. A quick note here, this is a material files. As you know, you can open them with any text editor. If you want to use a material for an electromagnetic simulation, you have to make sure you have the MATLAB block here added to it. Okay. In case you are not sure if your material is good for this type of simulation, please go to the supported software and make sure the MATLAB is on. Okay. Yeah, so now I'm going to go ahead. I don't know if you have Forge in your computer, but I'm going to open the tutorial coupled induction. So in case you want to follow with your computer, please go ahead, open Forge. If you have two screens, of course. Yeah, so this is how the tutorial looks when we open it. First thing we observe is we have a new object called Global Mesh. We'll have all the standard objects, the inductor and the billet, and the air is the orange box you see on the outside. What we're going to do once we have defined our objects is use this global mesh, this new meshing needed for the this type of simulation. I'm going to go ahead and show you. It's a little complex to create, but we have a dedicated training for it. So in case the tutorials and the online help are not enough, I'll show later where they are and the options we have. We can do online trainings now that we are all supposed to stay home. We can go over this in a 2-hour online training should be enough to give you the basics and help you with all your doubts. So showing the meshing, I just added a clip in playing here. You'll see this global mesh is taking into account all the other objects and combining them in a single mesh. One of the results here, well, I'll show you in the real case, but it's important that we get familiar with the global mesh. It's going to be the main difficulty for this new type of simulation. If we go to the induction heating, the thermal simulation, we'll see there's nothing special about it. It's just the standard simulation we are used to. In the process tab, you'll see we don't have a one direction arrow. We have a loop here. This means we're going to be jumping between solvers depending on the coupling parameters we specify. The second main thing to define is going to be the electromagnetic coupling. We need to decide how often we want to jump between solvers to update the electromagnetic parameters on the new temperatures in the billet. We have several options. The main option we use is the temperature. We'll tell the solver when we increase the temperature 300 degrees, please go back to the electromagnetic solver and update the electromagnetic parameters to make sure I have accurate values for my heating source. Okay. Now, I wanted to show you a real case that has a lot of information on it. Here we have the inductor is the green object, okay? And we have also concentrators. These objects are used to concentrate and localize where the magnetic field is to intensify the magnetic field in a specific area in our part. So here, for example, if we move a little, if I check the temperature result, we can see the temperature is increasing in the area we are aiming with the concentrators, okay? The concentrators, the only thing you need to know is the material you use for them, and we will help you with the parameters. In this case, we use concentrators, we use the electromagnetic field, but we also added some quenching. It's an option that not many users are aware of. If we check this is the HTC with the ambient media, we see we have a value of 10 for the air, but we are adding some quenching with a spray, okay? And we are, in this case, we were quenching this area at the same time. It's done with a spray attached to the inductor device. And it's a really common setup, so I thought that it would be interesting for people to know that we can, in this case, it's a moving inductor tube. We have no limitation to move the inductor and simulate the heating. It's actually quite common to have moving inductors in this type of simulation. And at the same time, we're applying a boundary condition there to apply quenching to simulate the sprays that are acting after the heating. Also in this simulation, we added phase transformation. Is it possible to add this if you have the TTT information? I don't have time to get into that, but we can get into details later in a different webinar. We're going to be listening to you. We will do webinars based on the feedback we get. Quick show of the, we can show the different phases. As long as you have the TTT information, we can help you to add this to your material file. There's no limitation here to combine those blocks. If we go to the electromagnetic simulation, what we're going to see at the beginning is just a block like this. This is the global mesh. As you can see, we only have the global mesh in the results. And it's not going to make a lot of sense at first sight. If we go to the result, it has changed the name now. Now it's called index. You'll see that in the global mesh, every element and every node is assigned to a different object. For one, a value of 1 means billet, value of 2 means this concentrator. Every object has a number, okay? Even if it looks like we have one object, we have all the objects defined. It's just shown in a unique mesh. Here we'll have all the magnetic results. I don't have a lot of time to get into them, so I'm just going to quickly show them. And what I want to show is how the mesh adapts. So in this case, when we have a moving object, we want to do the coupling often because we need to update the moving inductor to the heat source. Here, when we move the inductors, what we're going to change, what is really important is the heat power. It's going to change. If we wouldn't update this meshing, we will stay with the first heating source there. So it wouldn't matter if the inductor is moving unless we update the electromagnetic simulation. Okay, this is a good example to see the reason for this update of the electromagnetic simulation. Again, I don't have a lot of time. I just wanted to show how this looks. So I'm gonna go back to the presentations. Also, you'll have two simulations to check the results. I haven't specified this. In the thermal simulation, in the standard thermomechanical solver, we will have all the standard results that we are used to: phase transformation, grain size, temperature, all those. And in the electromagnetic simulation, we'll have all the electromagnetic parameters. Okay, we won't see changes in temperature here. All of that will be shown in the thermomechanical simulation. Okay, so with this, I just wanted to show how this looks. I would recommend to go to the online help here. I'm going to quickly show how to access the tutorial. If we go to tutorials on the left, 3D, induction, you have 2 full tutorials about this process with a step-by-step explanation, really useful. Check it out if you are interested about this topic and you think it might help your company. But now I want to focus on the new features we have applied in induction. It's an important topic for the developers. They've been working really hard on it. If you tried to use induction a couple of years ago and you thought it was taking too much time in terms of computational time, we have improved that a lot. The computational time has gone down a lot. So I would recommend to go back to induction and try it again, because a lot of improvements have been applied in the solvers, and especially in the coupling between solvers. The main problem here was that moving the information from the electromagnetic to the thermal and from the thermal to the electromagnetic was taking a long time. The developers have found a way to optimize this process, and now the computational time has gone down a lot. So I would, for those users that thought this was taking too much time to implement it to their workflow, I would recommend to double check this and go back to induction, try again, ask us for help if you need it. It has improved a lot. I'm going to show some of the new functionalities. I'm not going to enter or to explain the solver improvements because they are really technical and it might take some time, but just keep in mind that the computational times have gone down a lot. For the new functionalities, for example, we have added the Biometric sensor. This is a way to control the process. Okay, we've seen some people using a laser to control the temperature in a point in the billet and controlling the process based on that. Now you can do this on Forge. So you have to specify the temperature you want to achieve in that point, and the solver or Forge will adapt the electromagnetic parameters of your inductor, current, frequency, to try to reach that temperature. Okay? Again, there's a lot to explain here, but just so you know, we have this functionality. We can control the process with a laser now, or with a point. Also, most induction simulations are related with movement. This is not a problem. It's how we normally run the induction simulations, and we can do pretty much every type of movement you have to apply. We can apply continuous movement or movement by steps. Okay, I'm just going to go ahead and show you some examples. This is an inductor going through, a billet going through an inductor moving. As I show in the real example, we'll be updating the electromagnetic simulation. It requires some steps to add the movement, but it's nothing complicated. Don't think it's going to be a headache. It's a smooth process. Also, we have added movement by steps. Sometimes we don't have continuous movement, and this might be a problem for the solver. So we have added multi-pass files to induction simulation. So in this case, for example, we are moving. Oh, this one is a better way to show it. we're moving 10 millimeters every 2 seconds, these rings, just to show how that it's possible. We added the multipass file. Yeah, this is just to show we can apply any type of movement. If it's not continuous, it's okay. We have implemented pretty much every kinematics you can apply in a standard forging simulation. So also, I want to talk about the piloting modes. Before, the traditional setup was, well, with piloting modes, I mean the information we need from our inductor to prepare the electromagnetic simulation. By default, or the first time we introduced this simulation, we could only use the current and the frequency in the inductor. And this proved to be a little challenging for companies to obtain. Getting the current in the inductor was not easy to get. There are some devices to achieve this. This is one example. If you want to get details about how to measure the current at some point, contact us, because we have tackled this issue before with other companies. There are solutions, and they are not expensive. These devices are not that expensive. But anyways, if we cannot get the current, we have several ways to pilot the simulation now. First change is now we can enter current dependent on time, so it doesn't have to be a constant current. Also, we can use the potential. We don't have to use current if we have the potential, because that's what we are entering in our real inductor. We can use the potential now, and we can use the power, pilot by power. This is to use the parameters or the circuit for our generator. Again, this is too complex to explain now, but we have several schemes for this. And we've seen many customers prefer to use these because they're using the real parameters in the generator of the equivalent circuit, and the process is being regulated by this. And with the process, I mean the parameters in the inductor. Also, we have introduced self-induction. By default, in Forge, in the first versions, we were assuming that the electromagnetic wasn't affecting the inductor itself. This is a big assumption, and we were seeing that there were significant issues in some cases. Sometimes difference in temperature to 50 to 100 degrees. Now we have the possibility to simulate the effect of the induction process in the inductor itself. You have to activate the auto induction there. There's nothing to set up, just activate it. It will increase the computational time, of course, because we're adding elements to the equations, to the Maxwell equations. It is always more computational demanding. And what we are going to see is that the real current density goes to one side, the side closer to the part, and it will normally increase the temperature in the part. I have an example here from a real case. These are the inductors on the bottom left. I haven't explained the skin effect, but basically the current density is going to be higher in the skin of the objects. And in the inductors, you can see that the skin closest to the part is here, is this part. You'll get a lot higher current here, density, current density. And you can see the difference in this real case. This is the current density. It was a lot lower when we were ignoring the self-induction effect. Okay, and in this case, it was really important because the 50 degrees was being enough to don't create enough austenite for the process. It's a really important addition to the features you can use. Many customers were demanding this. With this, I want to bring awareness to the developers are always asking for feedback. So if you have any feedback or anything you're missing in Induction, please email us. I will show our email at the end. We have also implemented the possibility of using multiple inductors with different piloting modes. This is possible now. And the latest thing we have implemented are the Lorentz forces. Here we have an example, the electromagnetic process. The induction process normally creates some distortion in the inductors due to the Lorentz forces. We can get into detail this in trainings, but basically we will be able to simulate the distortion applied. This is amplified by 50, it's not there, so it looks higher than it is, but there's an important distortion due to these forces. Here you can see a quick summary. In Forge, all these features are applied for 3.0, Forge NXT 3.0. You won't see it in 2.1, so if you haven't updated yet, please go update as soon as possible. We have a lot of improvements applied in the solver, especially in induction, but also in all your simulations. I have mentioned the main features, and one of the features that will be applied in the commercial version in 4.0. But if you want to test it, we can set up a beta version for you to try these Lorentz forces. As I said, it's a really hot topic right now, so there are a lot of new features coming up. I will be updating you with new webinars. We're going to try to do a webinar every week now, depending on the feedback we get, to give you as much information as we can about the new features and about topics that we consider more important or that need some clarification. Yeah, this is all I wanted to talk about induction. A quick reminder, we have the online help. Again, you can access it from the interface, help. You will find 2 full tutorials and a lot of details about the new features applied. Also, Chapter 10 in reference documentation gives a lot of technical information about how the induction process is applied in Forge. This folder is by default in your Transvalor Solutions folder in the C drive. If you get in the Forge folder, documentations, reference documentation. Here you will find a lot of information. Check part 10 for more details about induction. Also, now that we are all staying at home, well, whoever can, we are offering customized online trainings. They are 2-hour sessions. You can have as many attendees as you want. We are really customizing it to each customer and company, so don't hesitate to contact us if you want more information on this. Now I want to go for the questions. I don't know, Nicolas, have you been checking the questions because I've been focused?
Yeah, thank you, Sergio. Seems that we have not had any questions on the chat. So what we're gonna do is, if you have any questions, we will recommend you email us at the support at transparamericas.com. You have it on your screen now at the bottom right. Please do not hesitate to contact us. It's the normal support email that you're used to. Again, so thank you all for being with us this morning. We hope you have enjoyed the webinar. Thank you again, Sergio, for the great work. It was really good. I hope a really good presentation. So we have recorded the webinar, as I said in the introduction, and we'll have it available for you in a member area. If you have not signed up yet, please go to www.transvaleusa.com and click on Members tab. Then sign up, and we will accept your request shortly after. We will communicate when the video is available. Next webinar will be about material data. We intend to split this topic with 2 webinars. We will communicate the final agenda for the next week webinar early next week. So the next webinar will be here next Friday at the same time. Stay tuned. We will send exactly the same process that you did for this webinar. We will also include some of the input we have received. So please feel free to click on the input link on the email we sent and provide us with some information about what you would like to see in the next webinar. Okay. So yeah, that's it. So stay tuned. Thank you again for joining us. There's actually just one question from Phil here about the next release of Forge NXT 4.0. So the 4.0 is scheduled for second quarter next year, okay? But before that, we'll have Forge NXT 3.1, which is scheduled for September this year, okay? With some mostly ergonomic features in the space. And then the major version 4.0 will be released next year, scheduled for second quarter. Okay. Thank you all again for being with us, and stay safe, stay home, and we'll be in touch. Again, if you have any requests, email us, and don't forget that we have online training scheduled or available for you. They are not scheduled actually; they are customized. So email us if you need training on a specific topic. We'll be happy to get you that. Okay. So thank you again, and you have a great day.